Okay. No, this doesn't move.
That one doesn't move. Just move the top, the bottom one up, or that one down.
Oh, there's another one.
Yeah.
Oh, great. Well, so I think I'd like to apologize in advance in that my lectures are pretty far from what most people here are thinking about. In fact, there will be very little, no algebraic topology, very little. So, well, so physicists have got a lot of mileage out of supersymmetric field theory, and they've been able to prove some very cool results. You know, like mirror symmetry, S-duality, which is a form of the Langlands conjecture, which says if I take n equals 4 gauge theory, for G is equal to the same thing the Langlands dual group, and so on. So it's long been a dream of mine to, this is still totally a dream, to formulate rigorously and maybe prove some of these duality results.
You mean like the physicist S-duality?
Exactly, yes. And this is like totally a dream. I think it's, you know, anything like this is kind of out of reach right now. Well,
formulate them mathematically.
Exactly, yes. Well, on the other hand, we already, you know, people do know something about these. Like people have done some great work on mirror symmetry, of course. However, most of the, so almost all map work on this kind of thing involves topologically twisted theories. So, well, so for example, like, you know, Donaldson theory, Gromov-Witten invariance, and the A and B models of mirror symmetry I mean, I say almost all because there has been some really nice work about two-dimensional theories which are not topologically twisted, like in the work of Peter and Stefan. I did a bit of work on that kind of stuff too. But anyway, so what I'm going to be interested in today are things in between the physical supersymmetric field theory and the topologically twisted supersymmetric field theory. I'm going to be interested in something called, like, which I call a minimal twist.
Can you say what that phrase, topologically twisted?
Yes, I will do later. It will take a lot of preparations. So, well, at a very kind of heuristic, big picture level, what's going on is this physical theory is roughly concerned with, say, the Riemannian or Kähler geometry of moduli spaces. This intermediate stuff, which I'm going to be interested in, is about the holomorphic geometry. And the topologically twisted things, this is roughly speaking, they're often about the algebraic topology of moduli spaces. For example, Gromov-Witten theory is about the cohomology of moduli spaces of maps from curves to a complex manifold. Donaldson theory is about the cohomology of moduli of bundles. Okay, so yes, so this. Anyway, so the aim of my lectures is to explain. I want to define what these minimally twisted field theories are, and then explain a bit how to construct them at the quantum level.
Can you say one more sentence about why physical theories require so much information?
You see this quantum. Let's see. Think of quantum mechanics. So quantum mechanics is a good example to think about it, because when you take any field theory on x cross OR and you reduce along x, it just becomes the OR direction just gives you quantum mechanics, but with an interesting target manifold which has to do with the moduli of equations of motion on x. So if I think of supersymmetric quantum mechanics on a manifold M, which in this procedure I said, yes. So this, if we're thinking of this as coming from some higher dimensional field theory, M will be some moduli space of bundles or something. And this has to do with, well, the Hilbert space involves spinors and the Dirac operator. I mean, of course, quantum mechanics involves a metric on M, like the heat flow. So if we consider, if you have a field theory on
Moduli space is what?
It'll depend on the data, but so suppose we have a field theory in x cross OR. So we reduce to a field theory on OR. Then what we're studying, roughly speaking, quantum mechanics on the space of solutions to the equations of motion on X. Okay, so I can't resist pointing out that one reason quantum field theory is kind of hard is that this space may be infinite dimensional. So, okay, so the goal of the lectures, maybe one, define classical field theory. Then I want to say something about supersymmetry in dimension 4. And the process of twisting. Describe these minimally twisted theories. Well, I'm really interested in supersymmetric gauge theories, and then finally maybe say something about what structure we see at the quantum level.
Is the idea that this program is motivated to dream of being able to formulate these duality results?
Exactly, yeah. And as we go left along this board, things get easier and easier. So the hope is that we could say something concrete about these duality results here, even if doing it over here is out of reach. Maybe another point about this diagram. So the physical theory knows about all of these. However, the part of the physical theory, this twisted field theory gives us some information, but not all about the physical theory. Okay, so what is a classical field theory? So I'm going to give a kind of fancy definition which doesn't involve any Lagrangians. I tried to talk a bit about this when I was in Stony Brook last year at Dennis's 70th birthday conference. Actually, my aim then was also to try and explain some of these things, but I never got anywhere near where I wanted to go. So at that time, I think I just got to there. So this time I'm going to go faster. Resist all. Suppose we have M as a manifold. So first I want to give you a kind of a very fancy definition of what a classical field theory should be, but this definition is a bit hard to make precise, at least for me. So a classical field theory on M is a sheaf on M, but a sheaf taking values in some very fancy category, so a sheaf of derived stacks of some kind. Equipped with a Poisson structure. Okay, so this is a definition I don't really know how to make sense of, because these things, well, the idea is this should be the space of solutions to the equations of motion, and that's maybe some kind of infinite dimensional thing, and then gets a bit gnarly. However, if we're willing to simplify things a little bit, we can get more concrete.
On such a space of solutions.
This quotes? Or is the...
No.
Oh! Yes. I tried to explain this in Stony Brook. It's the space of solutions is the critical locus of a functional. It's the derived critical locus. And anytime you have a derived critical locus, you have this structure. So it's part of the BV formalism, if you like. So the bracket is the extra structure telling you that this just wasn't some random sheaf of spaces. It actually came from the critical locus. I mean, that's the extra stuff you need to talk about, to try to quantize. Okay. So this is a bit hard to make sense of, at least for me. So to make things a bit easier, I'll define a perturbative classical field theory. Well, so
It's like instead.
yeah, I mean, we'll get a bit towards this more fancy definition we want later, but for now, let's stick with the perturbative definition. So I need to make this definition, I need to recall the how deformation theory works. So if X is a derived stack, and don't worry if you don't really know what this means. If I take a point in it, then there's an DG Lie, or L infinity if you prefer.
Fancy words, derived stack. I mean, can you, like in ordinary English, it's like some set of something with an equivalence relation on it that's like the solutions of something.
Yeah, exactly. It's exactly, yeah. But I mean, when we make things perturbatively, we'll just say it's just a Lie algebra. It's much more concrete.
Okay.
So if we have a guy, it's a derived stack, then I can take, say, the tangent space at a point with a shift of -1. So there's this DG Lie structure on, and this Lie algebra structure knows everything about the formal neighborhood of X. So I think Joey's going to talk about this week, right? This kind of thing. And so this is just Jacob's Diag 10. Also your ICM talk, which is very nice. And Joey's, how do you spell your last name? H-I-O-R-C-H?
No C.
Thesis. Okay. So as a replacement for all these things which I find hard to define, we're just going to say, well, suppose we just work near a given solution of the equations in motion, then all we have is a Lie algebra. So if we work near a given section, a sheaf of derived stacks, can be replaced by just a sheaf of DG Lie algebras. So what I'd like to do, I'll give a definition of the kind of DG Lie algebra I want, and then I'll give some examples.
Section means one equation, solution of the equation of motion.
Yeah, globally on the whole manifold. And then we just work in a formal neighborhood of that. So we're just perturbing that. And, so following definition. An elliptic differential graded Lie algebra on M is a sheaf of Lie algebras, DG Lie algebras, is a curly L such that, say, well, just to be precise, these will be of some analytic in nature, so these will be topological vector spaces. So, firstly, L, well, there's a graded vector bundle. where this guy is just the sheaf of sections, while the structure maps are differential operators, that actually follows. So D is a differential operator. The bracket is bidifferential. And finally, some technical condition that this is an elliptic complex. Oops. Yeah. Oh, hey, here.
Why do you expect the space of sections to be, underlined by an actual graded vector bundle as opposed to a sheaf of graded vector spaces?
Well, it's kind of technical, right? I want to do some kind of, when you want to quantize a theory, you want to do some kind of analysis, and for an arbitrary sheaf of topological vector spaces, you just lose all control. So, what's the point? If I take any vector bundle and I look at the sheaf of sections, if I could continuous endomorphisms of that are given by differential operators. So there's really, passing from L to its sheaf of sections doesn't really lose much information as far as we're concerned. So yeah, if you're not happy with those conditions, they're just kind of technical to make stuff work. So here's an example. Suppose X is a complex manifold. And P2X is a holomorphic G bundle. Then I can take the Dolbeault complex with coefficients in the adjoint bundle of Lie algebras. This is an elliptic DGLA, and this corresponds to the formal moduli problem of deformations of P, corresponding to, the moduli of holomorphic G bundles but near P. Okay.
So your general discussion before, this is the kind of example you kind of have in the back of your mind?
Exactly, yeah. You take some nice elliptic equation like ASD equations, with equations being holomorphic, with the derived moduli space of solutions. And then, there's always some nice elliptic complex describing a small neighborhood of every point.
So that word elliptic that you said was something technical but suppressed, it has something to do with solutions to an elliptic
Exactly.
differential equation?
Yeah.
Somehow this is modeling the solutions to them or something?
Exactly. If this was a two-term complex, then D would be an elliptic operator. This is just a generalization of the concept of elliptic operator to when you have a more than two-term complex.
Can you repeat? So this was the Dolbeault complex of X coefficients and what is G sub P?
Oh, so this is the adjoint bundle of Lie algebras. So the group G acts on the Lie algebra side. Okay, so there are many other examples along these lines. So I want to get on to definition of a classical field theory. So if you look back at our ideal definition, so we've managed to successfully, simplify the first part to say this is just a sheaf of DG Lie algebras, some properties, the second part, you can ask, what's the Poisson structure? So, yeah, I always seem to get tangled up in definitions when I give these lectures. I don't know. Well, suppose too many things are called X, but suppose that X is a derived stack. Yeah.
The shift. I mean, here you some of these brackets would help, but this Lie algebra structure does not help.
Oh, but the point is that H1 of this complex is the tangent space. You know, H1 is a class in H1 deforms a holomorphic bundle. So that's where the shift is. Suppose that X is a derived stack, which is symplectic. Whatever that means. Then the tangent space at X will have an antisymmetric pairing. So that the shifted tangent space will have a symmetric pairing. Now, it turns out that you can always arrange, that's not, wait, so that this is invariant for the Lie bracket. So we see that when we translate from this derived stack to a sheaf of Lie algebras, the Poisson structure will become some kind of invariant pairing on my Lie algebra. But pardon?
The example is just a two-metric
To
pairing.
I didn't understand.
What is the pairing in this case?
Oh, in this case.
There's just a two-metric.
Oh no, in this case there isn't actually a pairing. This is a case which doesn't have a pairing. It's just. So an example of something with a pairing. Three-manifold. I take a flat G bundle on M. Then this guy describes moduli of flat bundles and has a pairing.
What's the superscript?
Here?
Yeah.
Omega star, just the RAM complex. Yes. And it just comes from the usual Poincare pairing.
Don't you need that flat bundle to have a teeny bit of like
To have
a pairing like that?
well, you need G to be. This is a semi-simple Lie algebra, semi-simple Lie group, and we use the killing form on G on the. Okay, so this example should motivate our definition. I'm sorry, how am I doing for time? Is there? Okay, so this example motivates the definition. Well, if L is an elliptic DGLA, we let L shriek be the sheaf of sections, sorry again for all the notation, we take the bundle tensor densities. This is actually, if you like this kind of thing, the Verdier dual. So a pairing is an isomorphism between G and G dual. So we need to tell you what dual is. The correct notion of dual is the Verdier dual. So an invariant pairing on L is an isomorphism of degree k of L modules from L to this Verdier dual.
Are the densities then that are showing up somehow secretly like Lagrangian?
Yes, I suppose so, if you like. But we're not going to actually use the Lagrangian. We're going to integrate it. So,
Well, fine.
I mean, this is just showing up to say that there's some kind of pairing between compactly supported sections of this and compactly supported sections of this. I just pair the sections and integrate.
Does that number k interact with the dimension of the manifold?
No. So this is a bit different from the balance and Drinfeld story.
So the structure that you've said so far, if you had like a point,
Yes.
you could pull all that structure back to a point.
Yes.
This kind of structure, if you wanted to pull back to a point, wouldn't change by the dimension of the manifold?
No, I mean, I always want this to be -3 to give a classical field theory. So it will always be, when I take, say, cochains of this Lie algebra, will always have a Poisson bracket of degree 1.
Are you saying you can pull these things back?
I mean, well, of course, pullback is not compatible with Verdier dual unless you do some kind of fancy pullback. So.
But it is with a shift by the...
Okay. Good. Okay.
Could you repeat the question, Kevin?
Well, Jacob was asking, can we pull these structures back? And he pointed out that if you pull back with the correct shift, then pullback is compatible with Verdier dual, so you can. Okay, so isomorphism of L modules, L shriek to the K, which is symmetric. So a classical field theory is something with a pairing of degree -3. Oh, sorry again for. Okay. So that's just to make sure we have some kind of feeling for this definition. Check that it really holds for Chern-Simons theory. So, for example, if L is forms on M is again a 3-manifold, coefficients in GP. Well, L shriek, well, what we do when we take the dual of something, so the operation involved taking the dual and then tensoring with densities. So the dual of omega 3 is just, functions, but then I tensor with densities to get omega 3 again. So you see that L shriek is just L the shift of 3. No, hold on. So, I'm sorry, I said something wrong. So the way we set it up is compactly supported sections of this and compactly supported sections of this pair with each other naturally. So while omega 0 pairs with omega 3, omega 1 pairs with omega 2, and so on. So this is why this bottom row is the dual in the sense of the top row. Make sense? Great. So now we do indeed have a pairing of the correct degree.
Is this sort of like taking a manifold and the differential forms and the multi-vector fields in a volume form, putting the multi-vector fields in negative dimensions, and then using the duality pairing?
It is exactly that. Yes. Yes. Yeah.
So the duality pairing you described seems like it's saying that you have a two-form. So where is the closedness?
Oh, that's the condition that is invariant. So if you take the definition of two-form given by of symplectic form given by tau n of those guys, there's a Darboux lemma which says you can always change coordinates so it has constant coefficients, and the closedness says it's invariant. Make sense?
I mean, it seems like without saying it's invariant, you're saying you have a pairing on the tangent space at the identity, and saying
Exactly.
it's invariant is saying that you have one over the entire.
Yes.
But I don't see why it's saying that something's closed.
Oh, I mean, let's take G to be some finite dimensional Lie algebra. So then we have an element, as you say, we have a two-form like this. Okay, so the complex of two forms is this guy, and what we're saying, just take the two forms we're interested in are just the ones which have constant coefficients. Okay. So if I have an element of S2 of G star, I just extend it. I think that is an element of cochains of G with coefficients in S2 of G star. Now, there's two things we can ask. Firstly, that is closed for the differential on two forms. This is the condition is invariant. And then the second thing we can ask is that it's closed for the Ram differential. That's automatic because it has constant coefficients. Make sense? I mean, the Ram differential goes like that, with some shifts, and clearly this. Actually, maybe, sorry, one other point I should mention. When I said the Verdier dual, you need to use the topology to make this correct, so maybe that answers your question.
So you define the classical field theory to have degree minus 3?
Yes.
And we're working in 3 dimensions. Is that particular to 3 dimensions, or is that?
So he asked, does the fact that a classical field theory is a pairing of degree minus 3 relate to the fact we're working in 3 dimensions? The answer is no. This corresponds to the fact that suppose that X, or to some derived stack, has a Poisson structure of degree 1. Then it has a symplectic structure of degree minus 1. So that's a pairing on this guy of degree minus 1. And now when we remove these shifts, it becomes a pairing of degree minus 3. So in other words, the fact that I said minus 3 is the correct degree just corresponds to the fact that in the BV formalism, we want brackets of degree 1. Okay. Great. So this is, yeah. So far we have a definition of a classical field theory, even if it's a little bit abstract. You can see that what kind of features you want, just some invariant pairing on this Lie algebra, like omega 1 pairs with omega 2, that kind of thing. So I want to give more examples. So, well, a classical field theory is some kind of symplectic thing. And in ordinary geometry, we know the easiest way to construct symplectic things is as cotangent bundles. So there's a similar construction here. Suppose I take any elliptic DGLA, then the cotangent field theory where I just add on a copy of the dual. Okay, so why would you do something like this? Well, so if you remember, deformation theory tells us that we should think of L as some kind of sheaf of spaces. So this corresponds in the language of derived stacks to replacing x by some shifted cotangent bundle of x, which, of course, automatically has a symplectic form of the correct degree. Okay, so just like symplectic cotangent bundles are the simplest, most natural class of symplectic manifolds, cotangent field theories are, for me, maybe the simplest class of classical field theories. Great. So let's give you one quick example of a cotangent field theory, which we will see later corresponds to a certain supersymmetric gauge theory. Suppose that X is a complex surface and I take L to be this example again. Then the cotangent field theory is omega star GP plus omega with a shift of 1. So I just add on something which is the dual, and how do I get the dual of 0 k forms? It's k n minus k forms. So that's why we have the canonical bundle here. So the corresponding moduli space the moduli of G bundles on X with some adjoint valued section of the canonical bundle. Okay. So any more questions about classical field theory before move on to saying a little bit about supersymmetry. Happy? Happy or everybody seems happy or totally lost, and both of those are. Okay, well. Well, so a supersymmetric field theory on row 4 is a field theory, a classical field theory in the sense we defined. With an action of spin 4, of course, but also this is just what would you expect for any field theory in O4 that a physicist would like. But you want an extension of this action, an extension at the level of Lie algebras to a certain Z/2 graded Lie algebra which I'll now define. So we call that spin 4 is 2 copies of SU2. We let S plus and S minus be the fundamental 2 complex dimensional representations of the 2 copies. We let V be the fundamental rep of spin 4. So then, when I tensor with C, say VC, there's an isomorphism between this tensoring with complexification of V and S plus tensor S minus as spin 4 representations. So this allows us to define a certain DG Lie algebra. So this DG Lie algebra is called the n equals 1 supertranslation algebra. T n equals 1. Sorry, it's not DG, it's Z/2 graded. The Z/2 graded the algebra, which is just VC ordinary translations in even degree, and in the odd part, it's just the direct sum of the 2 spin representations. And the bracket wow. is this map from S plus tends from S minus to VC, which we wrote down before. In other words, if I take some element of S plus, some element of S minus, then their bracket is the image in their image in this translation guy. All other brackets vanish. Okay, make sense? Okay, so evidently spin 4 acts on this guy. So I can form the Lie algebra of spin 4 acts on this guy. So a SUSY field theory is one where spin 4C semi-direct product Tn equals 1 acts extending the action of spin 4 cross or 4. Okay, so I should make a couple of comments for this. You know, what sense does this make sense? So firstly, for this to make sense, our Lie algebra must be defined over C. And it also, well, this is a Z over 2 graded Lie algebra, whereas we were thinking of our classical field theories as being Z graded objects. Well, what we should do is so this must be a GG Lie algebra in the category of cochain complexes of Z over 2 graded vector spaces. So this means that there's two gradings, homological and supersymmetric. Both contribute to the signs, but the differential always respects the supersymmetric one. So L is Z cross Z over 2 graded, but the differential and all other kind of homological structures is of degree 1, 0. Okay. Have we?
So this R4 is identified with the VC?
Yes.
Somehow is it part of VC? So
Exactly. Yeah. So the reason for this rigmarole is that the spin representations in Euclidean signature are only defined over C. So, let's see. Yeah, I wasn't sure when should I stop, or is Stefan here or not?
Yeah.
Ah.
You mean time-wise?
Yes.
I mean, it doesn't matter whether we talk 5 or 10 minutes longer if that's a better cutoff point, so it's up to you.
Yeah, well, maybe. So what I wanted to do next time was talk about twisting. I think that will maybe take 10 minutes to do right. So maybe we should stop, but people should make sure to remember what supersymmetry Lie algebra is, because we're going to be using that.
grading?
Pardon?
What's the other grading?
Some of your fields might be like fermions, that they will have cohomological degree 0 and kind of supersymmetry degree 1. So like all the actual physical fields will be in cohomological degree 0, but they may be mixed up even or not.
It looks like such a cotangent case theory. I mean, is this form? I mean, it seems that you have such C2 grading. Is it automatically supersymmetric?
That's a little different. I mean, wouldn't, because we in order to get the pairing has to be of degree. So he was asking about, do cotangent theories automatically have some Z/2 grading? Well, the point is the pairing is of degree minus 3, 0. So any cohomological stuff only sees this part. So then what you said doesn't quite work.
So the Z grading is not related to any R symmetry grading?
Good, excellent question. When we twist, what we're going to see is we use the R symmetry grading to lift the Z/2 grading to a Z grading. Like we need to use R symmetry to mix the gradings around.
But then it might raise the second question, which is much trickier. So in theories which are not conformal, R symmetry can be broken dynamically.
At the quantum level, yes. Okay.
Which you might repeat.
So his question was that for theories which are not conformal, such as the n=1 supersymmetric H theory in 4 dimensions, the R symmetry, which we'll talk about next time, doesn't exist at the quantum level. However, it is Q exact, where Q is the thing we twist by. So that.
Normally when I think of a SUSY theory in R4, I just think of like one vector space with all this structure. Can you elaborate on how you're thinking of it as a sheaf? Like, am I thinking of the global sections of the sheaf you have in mind?
You're thinking of the global sections, exactly. Because when you think of this vector space, it might involve sections of spinors, sections of omega 1 for a connection, all that stuff. So we just take the sheaf of sections.
So usually I have some sort of like manifest, symmetry on this with the saturation spin 4, so that's just some combination of acting on the underlying space R4.
Exactly. Mm-hmm.
This degree minus 3 is still puzzling me. I mean, if I take some real baby example, which is like, Newtonian mechanics and Lagrangian formalism on R2, and I have the usual, Poisson pairing that one gets on functions on the cotangent space, where is the degree minus 3 pairing?
Well,
is there some explicit
what you're
thing
thinking
that it is?
when you said like functions of the cotangent space, you're doing a funny thing, which is you're looking at the equations of motion on codimension 1. So we're really looking at a particle moving in some manifold.
Yeah.
And what we're saying is that this sheaf on the real line has this degree minus +1 Poisson bracket. But if I look at the equations of motion, germs just at a point, there's some shift involved when you go down. That's what you're. Make any sense to you?
No, but I'll think about it.
Okay. Yeah, I guess so.
No further questions. Let's thank you again.
Thank you.